Today we're going to have a go at oxidizing the cyclohexanone we made in a previous video to adipic acid, a 6-carbon double carboxylic acid. We're going to use potassium permanganate as the oxidizing agent. First we wanted to check out just how exothermic this reaction could be, given that permanganate can be a very powerful oxidizing agent. Here's some potassium permanganate and a few drops of neat cyclohexanone. The good news is that it's not hyperbolic, there's no spontaneous ignition. Let's give it a helping hand. We're going to have to tame this oxidation process, and do it with some care. So here's our setup. We're using the 500 ml flask, and we've got a stir bar and a thermometer in there so that we can carefully monitor the temperature. We're going to use 150 ml of water as a solvent to perform the reaction in. Since our product is slightly soluble in water, we have a difficult choice. Too much water and our yields will be low. Too little and we could have a runaway reaction. Let's get the water into the reaction flask. We're using slightly warm water at 40 degrees because we want any reaction to kick off quickly so we know where we stand with it. Now for our oxidizing agent. Here's 32 grams of potassium permanganate crystals. This is a 2 molar ratio with the cyclohexanone we'll be using. Here's our reaction flask stirring away. Now we'll add the permanganate crystal to the water. Not all of them will dissolve at this temperature, but that's okay. Once they're all added, we measure out 0.5 grams of solid sodium hydroxide. And we're going to make a solution using 5 ml of water. The permanganate isn't going to react with the actual ketone group of our cyclohexanone. Instead it's going to react with the double bond present in the indole form of the ketone. By adding a little alkali and raising the pH of the reaction mixture, we increase the amount of indole form and so hopefully catalyze the reaction a bit. So we've added our sodium hydroxide solution and now we're ready. Here's our cyclohexanone. We've weighed out 10 grams into a small beaker. Check out our previous video for more details of how we made this starting from cyclohexanol. We're going to start off slow, so we're going to use a dropper to add the cyclohexanone to the reaction mixture. We're starting with about 3/4 of a milk. With stirring on vigorously, we're just going to watch the temperature and see if we can see a reaction. It takes a few minutes, but we start to see a slow but steady increase. There's slight brown tint appearing in the reaction mixture as well. The reaction is slow, but it's pretty relentless. After about 6 or 7 minutes the temperature had steadily climbed and was about 60 degrees C. So at this point we decided to apply some cooling to the flask. We started with an ice pack, but this didn't seem to have much of an effect. So we used a bowl of ice water. And at this point the reaction seemed to be finished and the temperature slowly came back down again. So we added about another ml of the cyclohexanone to the reaction mixture. This time we kept the flask in the cooling water. And after a few minutes, the temperature started to rise again. The second and subsequent additions weren't as vigorous as the first, and we managed to add all of the cyclohexanone to the reaction mixture in 4 batches over about 40 minutes. Here's the reaction mixture at the end. We allowed to stir for another hour as it cooled down slowly to room temperature. We added a drop of the reaction mixture to a beaker containing water. no purple permanganate color. So it looks like this show's over. Here's the cooled reaction mixture. Lots of brown suspended manganese dioxide in it. So we set up for filtration to get rid of this. We've got a clear filtrate, but it's a slightly red color. We're pretty sure this is due to a dirty filter as a consequence of our previous Henry reaction video. The red color is very difficult to get rid of. To clean the flask and anything else that has come into contact with the brown reaction mixture, we prepared a strong solution of sodium bisulfite in water. The flask is a bit of a mess, as you can see, but the bisulfite solution reduces the brown manganese dioxide and makes cleaning it much easier. Left in the filter is the brown precipitate of manganese dioxide. Save this because you can't turn it into active manganese dioxide, which is a useful oxidizing agent. Here's our filtrate. Yours should hopefully be nice and colorless if you used a clear filter. Along with decomposition products and products of side reactions, this hopefully contains our adipic acid in the form of the sodium and potassium salt. We're now going to add concentrated hydrochloric acid to this in order to generate the acid. There's a little effervescence, which we assume is because one of the oxidation byproducts would have been carbon dioxide, which would have then reacted with the alkali present to form a carbonate salt. On adding the acid, the red color turns yellow, indicating that it is an impurity from the filter from our previous reaction. We've added about 10 mL of acid, so let's test the pH. Strongly acidic, so we'll assume at this point that all our adipic acid is present in the solution as the free acid. Since the acid is soluble in warm water but not very soluble in cold water, we're going to chill the mixture down now and see if our product crystallizes out. After an hour of chilling, here we are. There's a white crystalline precipitate in the bottom of the beaker. So we set up for filtration again. We washed the product with a little ice water, and then dried it thoroughly on the pump. And here's our dry product. 3.5 grams of adipic acid. This is only a 24% yield on the starting cyclohexanone, so it's possible that we haven't quite got the reaction conditions right or the stoichiometry correct. In addition, some of the product will have stayed dissolved in the liquid due to its solubility. But it's nice and crystalline and seems quite pure. If you're going to try this reaction, then be careful because even though the reaction is slow, it's difficult to control even with cooling. Go very slowly, and take extra care if you scale up. Stay tuned to see what we've got planned for our adipic acid.